Modeling with functions. In this video, we'll be looking at functions from formulas, functions from graphs, functions from verbal descriptions, and functions from data. We've been looking at the basic functions. Now we're going to apply these functions to real-world problems. The first problem we're going to look at is a classic maximum value problem. The problem is, if we're given a piece of cardboard, what's the largest volume box that we can make? On the cardboard, to make a box, you need to cut out squares from each corner so that you can fold it up to make a box. This is what we are working with. We have the cardboard, we're going to cut out those squares, and we're going to make a box. So as part of that, first we need to write the volume as a function of x, find the domain of the volume, graph the volume. We're going to use the calculators to find the maximum, or we're going to use the maximum finder on the calculators to determine the maximum volume such a box can hold, and then we'll know how big the square should be in order to make the box of maximum volume. And I'll walk you through all this. So starting off with our volume. The first thing we're going to do is find the formula. So let's look at the dimensions here. We have an 8 by 15 piece of cardboard. So that's 8 and that's 15. Then we want to know how big these squares should be that we're going to cut out. It's a square, so it's x by x. And we're going to cut the same size square out of each side, each corner. So we're going to get a box. Our height is going to be x. The width here is going to be 8, but we're taking away 2 x's. So it's going to be 8 minus 2x. And that's where most people make mistakes. They will write it as 8 minus 1x, but there's 2 x's to take out. And the same thing on the length here. We have 15, but we're going to take away 2 x's, one on either end. So the volume of a box is length times width times height. So we're going to have 8 minus 2x, which is our length or width. It really doesn't matter. The other dimension is 15 minus 2x, and the height is x. So this right here is our volume, our function in terms of x. The next thing we need to do is consider the domain. The domain is what could the x's possibly be. When we're dealing with a box, we don't want the sides to be negative values. We don't want the height to be of negative value or either the sides. So we know that x has to be greater than or equal to 0. We know that 8 minus 2x has to be greater than or equal to 0. And 15 minus 2x has to be greater than or equal to 0. So solving these, I'm going to clear all this off. So I have x is greater than or equal to 0. 8 minus 2x is greater than or equal to 0. And 15 minus 2x is greater than or equal to 0. So solving this, I have a negative 2x is greater than or equal to negative 8. Dividing by negative 2, don't forget to switch the sign. X is less than or equal to a positive 4. Negative 2x is greater than or equal to negative 15. Dividing by negative 2 again, x is less than or equal to a positive 7.5. So setting up a number line here, I know that I want x to be greater than 0. It's going to go off in that direction. I know that I want it to be less than 4. It can include 4. And less than 7.5. Well, it has to be less than 4, so anything between 4 and 7.5 doesn't work. So the domain of this is going to be 0 to 4, with the 0 and the 4 both giving the volume of 0 for the box. But anything in between will give us a volume for the box. Now we're going to put it into our calculator and find the maximum value for x. So we'll go to our y is equal to, and clear out anything that's in there, and we're going to put in our formula. We have x times 8 minus 2x and 15 minus 2x. So in graphing this, because we already know our domain, we can go to our window and we can set our x minimum at 0 and our maximum at 4. The y stands for the volume. So the volume has to be a minimum of 0 because we can't have a negative volume. If we have a maximum of 8 by 15, 8 times 15 is 120. So that's the maximum that it could possibly be. So we'll set that as our y maximum. And we'll graph it. And we have a nice looking parabolic shape. What we want to do is find out what the maximum value is at the peak. So we're going to trace, so it's second and calc, and we want the maximum, enter, left bound, so use the arrows, go left of the peak, anywhere over to the left, enter, and arrow key over to the right of the peak, and enter for the guess, and there we have a maximum. Our maximum volume is going to be 90.74, and the maximum side of the x's is 1.66, so the maximum side of the squares that we cut out is going to be 1 2/3 inches. The next thing we're going to do is we're going to look at our calculators, and we're going to be doing some new things. So make sure you have your calculators out and you're following along with what I'm doing. You'll have to be pausing the video as we go along so you can enter the data. What we're going to do is we're going to be given a set of data points, and we're going to make a formula that fits those points. The first thing we'll do is make a scatter plot. The next thing we need to do is determine from the shape of the plot what kind of function that we're going to be using. Do we want a line? Do we want a parabola? Is it a cubic looking function? Is it a sine curve? And then we will perform what's called a regression, and that will give us a function that fits those points. We'll begin by looking at this table. The table that shows a number of patent applications in the United States from 1993 to 2003. We're going to find a linear and quadratic regression model for the data and decide which one is a better model of the data. So getting out the calculators, we want to enter this information into the calculator, and we're going to enter it in a list. So we're going to start that with our stat button and enter for edit, and this gives us our lists. To enter this, in L1 we want to put our X's, which are the years, so we start putting in the dates, 1993, and enter 1994. Pause the video while you put in the rest. So you should be up to 2003 for actually the 11th, and then you have a blank for 12. Arrow over to L2, and we can put in the applications with 189.4 and enter, and pause the video while you put in the rest of them. L2 11, 367.0 and enter. And there we have our two lists. The next thing that we want to do is to make a scatter plot for these. And the way you do that is where it says stat plot, we go second and the y is equal to. This is our stat plot. We want to plot, hit enter, and enter again. That will turn the first plot on. Our X list is L1, our Y list is L2, and it's making little squares. So we'll graph this, and let's go back to Y equals, and turn this one off by going to the enter and equals. And then we need to go to zoom, and zoom stat is what we want, which is zoom 9, and enter. And you can see from this that I entered something incorrectly. So 1, 2, 3, my fourth data point looks incorrect. So I will go to my stat and edit. 1, 2, 3, 4, yeah, I got 21.6 instead of 211.6. So I'll correct that to 11.6 and graph, and there, that looks much better. So that is our scatter plot. The next thing we want to do is make a line that fits that. So I'm going to go second and quit and clear this off. And what we do is we find a regression. And the regression comes from, again, it comes from the stat. And this time it's the calc. And we have down here linear regression, which is a line, and quadratic regression. Remember, a quadratic equation will give us a parabola, so the quadratic regression will give us a parabolic shape. We want to start off with a linear regression. What we want to do on the linear regression is tell it where our data is. So on the data, we're going to go second and L1 for our x's. Then we use the comma. Second and L2 is the y's, and comma. Then we have to tell it it's going to make a formula. We have to tell it where that formula goes. That formula will go to y1. And the way we get that is we go to the variables, the vars key, which is variables, the y variables, enter, and there it gives us y1, so we hit enter again, and now we have our formula. The linear regression, going the x is at L1, the y is at L2, and then put it into y1, so we hit enter. It gives us the formula, and y is equal, and it has put the formula in there, and if we graph it, there's our line. The next thing we want to do is do a quadratic regression. So I am going to go back to my y1 and turn off this function, and second and quit. I want a quadratic function regression, so I go back to stat and calc and quadratic regression, and we do it the same way. We want it going L1, comma, second L2, comma, and then our variables this time, going over to y variables and function, we want to put this one into y2. So I hit enter and enter again, and it will figure out the formula for my quadratic regression. If I go to my y equals, you can see both of them are in there, y1 and y2. y2 is being graphed right now, and this is a line for y2, and that seems to fit much better. Go back to y1, turn the first formula, the first line back on, and you can see the both of them together. And the quadratic function seems to fit a little bit better. And now I'll leave you with, just for fun, a little cartoon. See you in class.